nanohub.org.
Online simulation and more for nanotechnology.
So, morning everyone. My name is Shaoshuai. I'm an assistant professor at Purdue AAE. So actually my background is more in system control and multi-agent networks. And I know that there are several experts in this field, like our guest Lina, and also Aldo, and also for my friend Shreyas. And so today we're talking about distributed resilience for a swarm of autonomous agents. And first, you may ask why we care about multi-agent swarms. So I will use a short video to show you.
Our brains are like one big swarm. One neuron on its own is pretty dumb, just like this lonely ant. But when ants swarm together, collective intelligence emerges. And when neurons talk with billions of other neurons, consciousness arises. Without any one thing in command, we somehow become self-aware, make decisions. All of those simple ants and neurons swarm together to create intelligent systems. And these robot swarms work the same way.
So this is a video I downloaded from online. So from this, you can see that actually the major reason why researchers start to utilize multi-agent swarms or care about multi-agent swarms is that, by enable a swarm of agent, or for example, a swarm of ants, a swarm of birds working as a cohesive whole, and the swarm could accomplish sophisticated tasks which is beyond to the capability of individuals, such as like migration and foraging for food. So, motivated by this swarm intelligence, researchers have to start to utilize a large group of autonomous robots or autonomous drones for complex tasks like search and rescue, monitoring a large area, and for information gathering. So the features of multi-agent swarms, and we could look at first each individual. It usually is mobile, autonomous, and especially low cost, and each agent can only access local information. But if you look at the whole swarm, it's usually large scale, and it's usually heterogeneous, meaning it can consist of multiple types of agents, that could be ground robots, air robots, or different types of drones. And also there are usually communication constraints to the information flow across the network, because each agent usually can only talk to its nearby neighbors. And this precludes centralized coordination and gives the right to distributed algorithm or distributed control, distributed optimizations. And so the key enabler for multi-agent swarms is distributed algorithms for control, optimization, and coordination. So the goal of distributed algorithms is to achieve global objectives through local coordinations. And by local coordination, we mean the sensing communication among nearby neighbor agents. By global objectives, it means the complicated tasks that the swarm need to solve. For example, exploration of the unknown, formation flight, cooperative sensing, and search and rescue. So there are several advantages of utilizing multi-agent swarms. First is especially distributed algorithm. It has a nice scalability, and because each agent only needs to coordinate with its nearby neighbors, and it have nice flexibility, and especially it's robust under individual nodes or communication failures, as long as your connectivity is there. This kind of strong dependence of the whole swarm, strong dependence on its local coordination, and also has some disadvantage. For example, the whole network is vulnerable to even attack to one node because there's strong dependency. If you fully control one node, and you could use the connection or the dependency to steer the whole network, do bad things for the cyber attack view. And so, for example, I could use a multi-robot rendezvous problem, means a bunch of robots want to gather together. This is the ideal case. There's no cyber attacks, and they will gather together or reach a consensus about its position. This is more like a simple using the convex combination with nearby neighbors rule. And it will convert to the same point. But when there is one node is under cyber attack, for example, fully controlled by attackers, and this attacker could insert, for example, sinusoid signal, and the whole group of this swarm will not to reach the same fixed position. It will be guided or impacted by even this single node. Then this raises a question of how should we achieve resilience for multi-agent swarms? By resilience here, we mean the ability to prepare, plan for, or recover from and adapt to adverse events. And the challenge here is not an easy problem. The challenge here comes from three aspects. First, for the agents, individual agents. Individual agents is low cost, so it's usually with very limited sensing processing capability. And also each agent can only talk or communicate or sense about its nearby neighbors. So only local information available. And for the cyber attacks part, so they could be highly mobile. For example, in vehicular networks, each vehicle is mobile. It is fully controlled by a cyber attack, and then it could connect itself to different other agents. And this is actually is worse than a cyber attack with a fixed location. And also, it's usually sophisticated, and it could fully control the normal agent and pretend to be good. So especially when each agent only has local information, it's hard for the normal agent to identify which one is malicious, and they isolate. And of course, and because we are more thinking about a large-scale swarm of agents, you already have a large scale of attacking surface, and multiple attacks could be launched massively from multiple locations. And also in the network side, and the network is usually time varying, because even we start from a fixed network. Because of the communication failures, the network could be dynamic, could be time varying. This is could lead to very challenging in design control to achieve the resilience. And from all these reasons, so we are motivated to develop techniques for resilience in multi-agent swarms must be automated. So it has to be, because your cyber attacks may be launched massively, and you need to respond very fast. And also you need to adapt to time-varying networks, and also time-varying attacks. And also, of course, in a fully distributed scenario, means there's no central controller. So, and in this direction, and we have done a little bit about consensus-based digital algorithms for its resilience. And this is a project funded by CRISP, and it's a joint research with my friend Shaoshuai Sandra. And so we more like co-supervise a PhD student working on this. We meet quite regularly, like at least one time every 2 weeks, 1 hour and 2 hours discussion. And so, okay, so you may ask why we care about consensus. So consensus means all agents reach agreement on some quantity of interest. This is the key enabler for swarm agents to work, especially to work as a cohesive whole. So there are three types, mainly three types of consensus in multi-agent swarms. First is unconstrained consensus, means all agent states reach the same value. For example, all UAVs need to fly in the same direction. So more like synchronization types. And then there may be constrained consensus, means all UAVs not only fly in the same direction, but this direction needs to be north. And there's also optimal constrained consensus, means all the UAVs need to fly in the same direction, fly north, and also need to adjust its speed to minimize the global cost function of the whole networks. But of course, by only local coordination. Each agent may not know what this global function look like. So there are tons of works in consensus-based digital optimization. I know Aldo, Lina, and Shreyas all have done very nice work. So a common structure for all the updates for consensus-based digital algorithm is this structure. So the state, so XIT here denotes each agent state. So a state is the the update for each agent I state utilize average, VI. VI is just a linear combination, a convex combination of its nearby neighbors. Almost all consensus-based district computation, district optimization, district control all utilize this convex combination with neighbor information. So if there's no separate attacks, it works perfectly. Many researchers have devised graphical conditions such that the algorithm to work. But even if there's one node, it's connected to malicious agents. And so the malicious agent could inject wrong informations through this average vector or through this local average. And this could easily cause a failure of consensus. So one node under one agent becomes malicious, means fully controlled by a cyber attacker, could lead to a failure of all the consensus-based digital algorithms. And then the question is reduced to how to exclude malicious information without knowing which one is malicious. For example, if I'm agent I receive a bunch of informations, but I don't know which one is malicious. And because I have limited sensing and computation capability, I even don't have the capability of identifying which one is malicious. So this is the question we want to answer. And this is actually not an easy problem. I will show you a simple example. For example, suppose agent I receive 4 pieces of information in the plane. It's all 2D. Suppose it knows at least one of them is malicious. And so how to exclude the information from a malicious one? So you may ask, let's do the majority rule, because X2, X3, X4 are all close together. It's very close to me. So agent 1, the information may be malicious. So this works for unconstrained consensus, and but whenever there's a constraints, more like, for example, we are trying to solve a large linear equation, and the state vector may why the location of agent 1 states is here, is far away from others, may come from its local constraints. So majority rules does not work here, especially we are considered constraint optimization. And so if you use majority rule, you will exclude X1. So any ideas for solve this problem? So this idea, we have one idea. So it's at least 25K. So which is funded by CRISP. So I will show you a little bit and what we have achieved, and you will see your money is well spent. So we have developed instead of using a simple convex combination, we have developed what we call the resilient average, means which is always a weighted average of normal agent states, no matter which one is malicious or no matter whether there is a malicious. So I only need to know one upper bound of how many malicious agents is nearby me. So this is a little bit of piece information, which is integer information, which is also local information. And then based on the information we received, we could come up with a convex combination, which is always resilient, means which is always combination of normal agents. So this is the key idea of this is we utilize, instead of utilize the simple average, we utilize the intersectional convex Hall. And so this enables us, don't need to, this requires no identification and isolation stuff. And we have done some simulation results on consensus-based digital computation and optimizations. And you can see we consider time-varying networks. And the malicious, the attackers is also time-varying. And also each agent only accessed to local information. And this is the curve that the potential function go to 0, means that all the errors go to 0. We achieve the goal. So this is accepted by a journal, Numerical Algebra Control and Optimization. It will to appear this year. And then based on this, maybe next step we will try to do to achieve some resilience for consensus-based, for example, district reinforcement learning things. And so this is a summary of what we have done. I hope you guys are happy. And so, and also, you may ask next step, how about whether there will be opportunity to integration with other techniques, especially, for example, AI and machine learning are so popular now. So, and there are some challenges. For example, always remember that we are considering a multi-agent swarm. Each agent is weak. is low cost. It may not have the capability to implement AML. And you may say, oh, let's involve human in the loop. And we have a large-scale multi-agent, so where and when we need to involve human in the loop. This may be addressed by actually the classical control theorem called structural actionability. And also maybe utilization of blockchain. I'm not expert blockchain, but I know that the cost will definitely increasing. For example, the proof of work, and I thought not that fully distributed. I guess Shucheng is an expert on that. We may talk about that. Of course, there are a lot of other questions to be answered, and that's why we are here, especially from NSF, and so to solve these questions. And then next, you may although there's for distributed control. So my expertise is in distributed control and distributed algorithms. So it's still an open problem to achieve resilience in fully distributed scenario. I will continue working on distributed algorithms for control optimization and local coordination because I like it and kind of powerful. First, it could serve as a top-down analysis to analyze very large-scale networks, like vehicular networks, social networks, transportation networks. As long as they are large-scale networks, there's no central controller, and then distributed algorithm could serve as the tool. And on the other hand, we could utilize distributed algorithm to serve as the bottom-up synthetic tool to build more powerful machines. So each single machine has its own capability. By connecting them together, making them working as a cohesive whole, we may get a more powerful machine. For example, one balloon cannot lift a house, but 1,000 one could. So this is all my talk. Thank you.
So we have time for a few questions. So you mentioned that some of the things you are thinking about machine learning algorithms and all, but not yet probably have made.
Not yet. It's just more.
But I wonder whether these two problems map in some way. Can one view each neuron to be one of your agents?
Yes.
And anytime one of the transistors in that neuron or the memory element in that neuron degrades, or because this is CMOS, either CMOS based or it's a resistive RAM type memory. So when one fails, it will be feeding wrong data to the neighbors. And if so, can the resiliency algorithms that you have for the swarm can map back to this, how to recover from failing nodes at the machine learning algorithm? I mean, I'm saying that these two problems may be mathematically equivalent.
A very good question. Is to be honest, we have not thought about that. And it's more like when the research problem goes from centralized to decentralized, which makes the problem much more challenging to solve. For example, even when you want to stabilize the 4-agent formation, if the topology is consists of 2 cycles, there's no solution to even stabilize it. And to go back to your question, that's why we only focus on small piece of consensus based on the multi-agent swarms. That is the consensus algorithm. And why we focus on consensus, more like which is has a lot of applications or serve for the fundamental mechanism for many other applications. For the consensus, and because to achieve consensus, the rule kind of simple. It just utilize the average. So I believe that's also very simple, almost the simplest update actually in multi-agent swarms. So that's why I guess we have achieved some result on that. For more complicated, we're not sure. So maybe in future, but for the more like utilize multi-agent techniques, especially distributed algorithms about multi-agent swarms into, for example, neurons or brain networks, it's definitely something we are very interested in. Actually, I give the talk in Washington University, St. Louis, and one of them will also propose similar questions. How to map all the techniques developed in MAS to the brain networks. Because we also have a large networks there. Thank you.